Good evening all, welcome to Unacademy. As Pavan, Bhargav, Sham, good evening. How are you all? Good evening, Arsha. Okay. నా వాయిస్ క్లియర్ ఉందామా? వినిపిస్తుందా క్లియర్ గా? Is my voice clear or not? Yes, Pavan, thank you. Raju, good evening. Okay, thank you. Welcome to Unacademy. This is Bhanu Prakash, expert in GATE and ESE. I did MTech from NIT Kurukshetra. I have 10 years of teaching experience and I trained many students for different competitive exams like GATE, ESE, TRANSCO and GENCO, and also some state electricity board exams. My interested subjects are electrical machines and power electronics. So this is BPC 10 is my referral code. By using this code you will get 10% discount on Unacademy subscription. All of you got it? So there are two types of the subscription. Okay. First subscription is the plus subscription and second one is iconic subscription. What are the benefits of the plus subscription? One is live classes. Okay, this is a first one is a the live classes. You will get live classes from the top educators. So here for one subject we have a more than 20 teachers, so that if you want you can get any lecture also. There is a choice of the teacher, so you can select the teacher as your choice. And next one, structural schedule. So that is we can plan your schedule for 3 months, 6 months, 12 months and also 24 months, and unlimited practice question for topic wise and also subject wise. And there is a test series. You will get the test series also if you take the plus subscription. Okay, got it? And in case of iconic subscription, in addition to these 4 benefits, okay, you will get some additional benefits. So that is the personal coach, study planner, expert guidance, and also ESC questions and answers. Okay, got it all of you? Josna, good evening. And this plus subscription is available. Okay, 6 months untundi, 12 months and also 24 months available ga undi. So na code is chesarankondi meeru BPC 10. This is my code. So make 10% discount vastadi. Ee 10%. Okay, this is the my code. The code is a BPC 10. So this is the my code. Okay, if you use this code you will get 10% discount. So after the discount you have to pay 22,500 rupees per 1 year subscription. and for iconic subscription, and it is available for 12 months only. For this is the 12-month fee is the 45,000 rupees. So if you use this code, you will get 10% to discount. So after the discount, you have to pay 40,500 rupees. Got it? So this is about the plus subscription and also iconic subscription. What are the payments method you can use? And you can pay directly, and also we have a payments, that is the EMI option also. For 3 months EMI, you per month fee is a 7,500 rupees. For 6 months EMI, per month fee is the 3,750 rupees. For 9 months EMI, 2,500 500 rupees. For 12 months EMI, the EMI per month EMI is 1,875 rupees. So this is about that is a per 1 month the fee structure, it is a 1,875 rupees. Okay, so ఈ 20 తర్వాత ఈ ఫీ అనేది ఇంక్రీజ్ అవుతుంది. సో చేశారు ఆల్రెడీ, డేట్ కూడా రివైల్ చేశారు. ఇఫ్ యూ వాంట్ టు టేక్ ద సబ్స్క్రిప్షన్, టేక్ ఇట్ బిఫోర్ 20 ఆఫ్ దిస్ మంత్. ఓకే, so it's a very year. Simply just if you take 1 year subscription, how much you have to pay for 1 month? It is 1,875 rupees. So this is my code BPC10. If you use this code, you will get 10% to discount. So after the discount, you have to pay 22,500 rupees. సో మీరు ఒకవేళ తీసుకోవాలని ఛాన్స్ ఉంటే ఈ 20 లోపు తీసుకోండి అమ్మా. మీరు ఒకవేళ ఆ తర్వాత తీసుకోవాలనుకోండి, ఇది డబుల్ అయ్యే ఛాన్సెస్ ఎక్కువ ఉంది కాబట్టి మీరు అప్పుడు తీసుకున్నా కూడా యూస్ కాదు. ఒకవేళ మీరు సెకండ్ ఇయర్ లో ఉన్నారనుకోండి, సెకండ్ ఇయర్ లో ఉంటే నేను థర్డ్ ఇయర్ లో తీసుకుందామని ఆలోచన ఉందనుకో, సెకండ్ ఇయర్ లోనే మీకు బెటర్. మీరు ఒకవేళ 2 years సబ్స్క్రిప్షన్ తీసుకున్నారు అనుకోండి, మీకు సెకండ్ ఇయర్ థర్డ్ ఇయర్ లో వస్తుంది. సో ఈ 2 years ఉంటుంది. తర్వాత ఈ 2 years తర్వాత నీకు గేట్ థర్డ్ ఇయర్ లో రాసినా కూడా నీకు యూజ్ అవుతుంది. సో మీరు తర్వాత నేను జనవరిలో తీసుకుందామని మీకు ఛాన్స్ ఉంది అనుకోండి, అప్పుడు కూడా ఫీ డబుల్ అవుతుంది కదా. మీరు తీసుకోవాలనే ఛాన్స్ ఉంటే ఇప్పటి నుంచే తీసుకోండి. సో మీకు ఒక 2 months ప్రిపరేషన్ యూజ్ అవుతుంది. am I right? Okay, this is about subscription methods, what are the benefits and also fee structures. Okay, all of it clear? Okay, is that clear everyone? Yes, very good. Next one, this is our Unacademy Gate Telugu team. సో ఈ టీమ్ లో ప్రజెంట్ ఇప్పుడు 5 members ఉన్నారు. శంకర్ సార్, ఓకే మీకు తెలుసు శంకర్ సార్ ఈ టీమ్ లీడర్. సో మీకు ఈ శంకర్ సార్ మీకు తెలుసు క్వాలిఫికేషన్ కూడా. శంకర్ సార్ ఐఐటి ఖరగ్పూర్కి వెళ్ళి ఎంటెక్ చేశాడు. సో నౌ పిహెచ్డి, నౌ ఈస్ డూయింగ్ పిహెచ్డి ఫ్రమ్ సెంట్రల్ యూనివర్సిటీ ట్రిపుల్ ఐటి హైదరాబాద్. అండ్ దిస్ ఈ డీల్స్, శంకర్ సార్ డీల్స్ ద నెట్వర్క్స్ అండ్ డిజిటల్. ఓకే, తర్వాత నెక్స్ట్ వన్ వెంకట్ కృష్ణ సార్. సో ఈ పిహెచ్డి సార్ కూడా ఎంటెక్ ఫ్రమ్ ఐఐటి ఖరగ్పూర్. సో సార్ మీ మ్యాథ్స్ చాలా బాగా చెప్తాడు. సో మీరు ఆ సార్ కూడా క్లాసెస్ వినండి, యూటిలైజ్ చేసుకోండి. తర్వాత శర్మ సార్ ఆప్టిట్యూడ్ చెప్తాడు. సార్ మీకు ఐఐఎంకి వెళ్ళి పాస్డ్ అవుట్. సో మీకు ఆప్టిట్యూడ్ క్లాసెస్ ఆల్రెడీ తెలుగు ఛానల్లో జరుగుతున్నాయి, మీరు కంపల్సరీ అటెండ్ కాండి. మీ గేట్ ప్రిపరేషన్ కానీ, మీ ఏ ఎగ్జామ్ ప్రిపరేషన్ కానీ ఆ సబ్జెక్ట్ మీకు చాలా యూజ్ అవుతుంది. సో ఈసీ పీపుల్, సో కమ్యూనికేషన్ సిస్టమ్ జరుగుతుంది ఇప్పుడు. సో నెక్స్ట్ సార్, ఓకే సార్ చెప్తాడు మీకు. సార్ నేమ్ నాగేశ్వర్ రెడ్డి. సో ఈజ్ పిహెచ్డి. సో మీకు కమ్యూనికేషన్స్ లో ఈసీ వాళ్ళకి మీ ఫ్రెండ్స్ కి షేర్ చేయండి ఇన్ఫర్మేషన్. ఓకే, అలా ఫిగర్ ఇట్ మై పాయింట్. సో ఈ సండే, ఈ సాటర్డే అండ్ సండే, ఓకే సాటర్డే అండ్ సండే క్రాస్ కోర్స్ స్టార్ట్ అవుతుంది. సో క్రాస్ కోర్స్ లో సో ఎవ్రీ సాటర్డే పవర్ ఎలక్ట్రానిక్స్ స్టార్ట్ అవుతుంది. ఓకే, డూ యూ నో Joseph, power electronics, right? Saturday, Sunday, power electronics. Okay, okay. రైట్, చెప్తాను, తెలుగులోనే చెప్తాను. కొన్ని టెక్నికల్ వర్డ్స్ ఉన్నాయి కదా, అందుకని చాలా సింపుల్ వర్డ్స్ లో చెప్తున్నా నేను. ఓకే, పవర్ ఎలక్ట్రానిక్స్ మిషన్స్ కన్నా కొంచెం డిఫికల్ట్ ఉంటుంది, అది నేను కంప్లీట్ గా తెలుగులోనే మీకు చెప్పడానికి ట్రై చేస్తాను. ఓకే, మిషన్స్ లో కొంచెం తిరిపాటు ఎక్కువ ఉంటుంది. సో అవన్నీ కూడా నేను మామూలుగా తెలుగు ఇంగ్లీష్ రెండు కంబైన్డ్ గా చెప్తున్నాను. సో మాక్సిమం ఒకవేళ డిఫికల్ట్ లెవెల్ ఎక్కడైతే ఉంటుందో నేను అది కంపల్సరీ తెలుగులోనే చెప్తాను. ఓకే జోషప్, కానీ మీరు స్టూడెంట్స్ కి షేర్ చేయాలా లైవ్ లో. మనకు ప్రతి లైవ్ క్లాస్ లో 100 మెంబర్స్ ఉండాలా. మీరు 10 మెంబర్స్ 10 to 12 ఉన్నారు అనుకోండి, మీరు ఇంకా 10 to 12 మెంబర్స్ తీసుకురావాలి అప్పుడు లైవ్ కు. సో నువ్వు లైవ్ క్లాసెస్ లో ఎక్కువ ఉన్నా అనుకో, మాకు కూడా కొంచెం ఎనర్జీ ఉంటుంది. సో మీరు అదే 1 2 మెంబర్స్ ఉన్నారు అనుకోండి, చాలా డల్ ఉంటుంది క్లాస్. రైట్. మీకు ఏ సబ్జెక్ట్ ఎంత లెవెల్ కావాలనేది అంతవరకు మేము చెప్తాం. సో మేము చాలా ఎక్స్పీరియన్స్ ఉంది, ఎంతో మందికి స్టూడెంట్ చూసినాం, ఆఫ్లైన్ లో చాలా బ్యాచెస్ చెప్పాము. కాకపోతే ఇక్కడ మేము ఆఫ్లైన్ లో మీరు ఒక జస్ట్ ఆలోచించండి, ఆఫ్లైన్ కోచింగ్స్ లో మీరు ఫీ కట్టి ఒక 200 మెంబర్స్ క్లాస్ లో ఉంటారు. సో అదే మేము ఫ్రీ చెప్తున్నాం కదా, సేమ్ టీచరే సేమ్ క్వాలిటీ నీకు ప్రొడ్యూస్ చేస్తున్నప్పుడు నువ్వెందుకు ఇక్కడ ఆఫ్లైన్ లో ఆన్లైన్ కు ఎంత మందికి రావట్లేదు? ఎలాగో ఇప్పుడు ఆఫ్లైన్ ఏం జరగట్లేదు కదా. రైట్. ఇక్కడ చెప్పిన వాళ్ళు ఎవరు కొత్త వాళ్ళు కాదు కదా, ఆఫ్లైన్ లో చాలా బిజీ ఉండి ప్రతి ఇయర్ ఒక 10 to 12 బ్యాచెస్ చెప్పేవాళ్ళం మేము. ఎస్ శ్యామ్, నువ్వు క్లాస్ అటెండ్ గా పవర్ ఎలక్ట్రానిక్స్ ఏంది అనేది నువ్వు తెలుసుకుంటావు. మిషన్స్ కన్నా ఇంకా చాలా బాగా చెప్తాం. పవర్ ఎలక్ట్రానిక్స్ లో ఏది డిఫికల్ట్, ఎక్కడ డిఫికల్ట్ అవన్నీ నాకు తెలుసు. స్టూడెంట్స్ కి ఎలా చెప్తే అర్థమవుతుంది. ఓకే, నేను ఎప్పుడు కూడా స్టూడెంట్స్ పాయింట్ ఆఫ్ వ్యూ ఆలోచించే క్లాస్ చెప్తాను. నా నాలెడ్జ్ నేను ఎంత లేకపోతే నేను ఎలా చెప్తా అనేది నేను చూపించుకోవడానికి క్లాస్ చెప్పట్లేదు. మీకు ఎలా యూజ్ అవుతుంది అనే పాయింట్ ఆఫ్ థింక్ చేసే మీకు క్లాస్ చెప్తాను. ఓకే, I don't want to show you this about me in front of you. Okay, just I want to deliver my content clearly to the students. Okay, which should be useful to your competitive exam side. ఆ పాయింట్ ఆఫ్ వ్యూలో నేను క్లాస్ చెప్తాను, స్టూడెంట్స్ పాయింట్ ఆఫ్ వ్యూలో మీకు అర్థం కావాలని. చాలా దాని ఇంకా బ్యాక్గ్రౌండ్ వర్క్ చేసి కొన్ని పిక్చర్స్ అవన్నీ డిజైన్ చేసి సో క్లాస్ మేము స్టార్ట్ చేస్తాం అలా. కానీ క్లాస్ లో వ్యూస్ రావాలి, ప్లస్ ఎట్ ద సేమ్ టైం లైవ్ లో 100 మెంబర్స్ ఉండాలి. ఐ వాంట్ టు సీ 100 మెంబర్స్ ఇన్ మై లైవ్ క్లాస్. అది డిపెండ్స్ అపాన్ యూ ఓన్లీ. మీరు ఎక్కువ మందికి షేర్ చేస్తే 100 మెంబర్స్ స్ట్రెంత్ వస్తుంది. శ్యామ్, ఐ రైట్? నీకు పవర్ ఎలక్ట్రానిక్స్ మిషన్స్ క్వశ్చన్ తర్వాత ఇంకా ఇప్పుడు పవర్ సిస్టమ్ మెజర్మెంట్స్ కూడా స్టార్ట్ అవుతాయి. కాకపోతే లైవ్ మీ స్ట్రెంగ్త్ పెంచాలి. స్ట్రెంగ్త్ పెడితే నెక్స్ట్ సబ్జెక్ట్ స్టార్ట్ చేస్తారు కదా. ఇప్పుడు మీరు ఈ స్ట్రెంగ్త్ చూపించాలి. మీకు మిషన్స్ క్వశ్చన్స్ కానీ పవర్ ఎలక్ట్రానిక్ క్వశ్చన్ కానీ నీకు ఫ్రీ కంటెంట్ అయినా కూడా నీకు కంప్లీట్ గా ఇస్తాం, కంప్లీట్. ఓకే రైట్. ఓకే గుడ్. ఎనీ మోర్ డౌట్? సో 50 hours అని క్రాస్ కోర్స్ లో ప్లాన్ చేశాను. నీకు 50 hours కావాలి, ఎక్కువైనా కూడా నేను తీసుకుంటాను, ప్రాబ్లం ఏం లేదు. డిసెంబర్ ఎండ్ ఆఫ్ ద డిసెంబర్ ఐ విల్ కంప్లీట్ ఇట్. శ్రీనివాస్, మీరు పవర్ ఎలక్ట్రానిక్స్ క్లాస్ రండి, మిషన్స్ క్లాస్ రండి, మీకు ఏ కంటెంట్ కూడా నువ్వు ఎక్కడ వెళ్ళినా కూడా తక్కువ కాదు. దట్స్ మై ప్రామిస్. ఓకే, ఆ కంట్రోల్ సిస్టమ్ కూడా చెప్తారు, కానీ ఇప్పుడు జరిగే సబ్జెక్టులకు స్ట్రెంగ్త్ చూపించాలి రాజు. కంట్రోల్ సిస్టమ్ కానీ నెట్వర్క్స్ కానీ డిజిటల్ అన్ని సబ్జెక్టు ప్రతి సబ్జెక్టు మీకు కంపల్సరీ యూట్యూబ్ లో టీచ్ చేస్తారు. కాకపోతే మనం ఇది చెప్పేది కూడా కంపెనీ తరపున కాబట్టి మీరు స్ట్రెంగ్త్ ఎక్కువ ఉండాలా. స్ట్రెంగ్త్ ఎక్కువ ఉంటే నెక్స్ట్ వేరే సబ్జెక్ట్ నీకు స్టార్ట్ చేస్తారు. ఇప్పుడు స్ట్రెంగ్తే లేదు, జరిగే సబ్జెక్టులకు స్ట్రెంగ్త్ లేనప్పుడు నెక్స్ట్ సబ్జెక్ట్ ఎలా స్టార్ట్ చేస్తారు? am I రైట్? మీకు ఇంట్రెస్ట్ లేదని అనుకుంటారు కదా. ఇప్పుడు యాక్చువల్లీ అన్అకాడమీ వాళ్ళు తెలుగు గేట్ అని స్టార్ట్ చేసినప్పుడు తెలుగులో స్ట్రెంగ్త్ ఎక్కువ ఉండాలి. యాక్చువల్లీ ఆ తెలుగు స్ట్రెంగ్త్ మీరు తక్కువ చూపిస్తున్నప్పుడు నెక్స్ట్ సబ్జెక్ట్ స్టార్ట్ చేయలేరు వాళ్ళు. ఓకే రైట్, లిజన్. So previous class we had discussed about the equivalent, that is a effect of the resistance, practical transformer effect of the resistance, and also practical transformer with effect of the leakage flux. So what will happen, the leak by using the leakage flux or by considering the leakage flux, some voltage drop takes place. Okay, meer resistance అండ్ లీకేజ్ ఫ్లక్స్ అనేది ప్రాక్టికల్ ట్రాన్స్ఫార్మర్ లో కన్సిడర్ చేసుకుంటే మనకు రెసిస్టెన్స్ ద్వారా వోల్టేజ్ డ్రాప్ లాసెస్ వస్తాయి. కానీ అదే లీకేజ్ ఫ్లక్స్ ద్వారా లాసెస్, దెర్ ఈస్ నో పవర్ లాస్, ఓన్లీ వోల్టేజ్ డ్రాప్ టేక్స్ ప్లేస్. సో హౌ డు వి రిప్రజెంట్ దిస్ డ్రాప్ హియర్? దట్ డ్రాప్ కెన్ బి రిప్రజెంటెడ్ by using the fictitious or imaginary element. So that is a I1 X1 drop and I2 X2 drop. Okay, so this part we had discussed in the previous class. So today we will discuss about one more the important topic for competitive exams. So that is the equivalent circuit of the circuit of single phase, the transformers. Okay, got it? Fine. So first question, what is mean by equivalent circuit? Okay, and how do we draw the equivalent circuit of transformers? So equivalent circuit is a electrical circuit representation of, okay, our cream point. So electrical circuit representation of all the parameters by using simple circuit elements is known as the equivalent circuit of the transformer. So what are the simple circuit elements like resistance, inductance, capacitance? So by using these parameters, we have to model the transformer. So that is known as the equivalent circuit of the transformers. Okay, got it? So how do we draw the equivalent circuit of transformer? And what are the parameters or quantities of the transformers here? So in case of transformer, let's see first one. Let us assume, so let V1 is a supply voltage of the transformer. So this is the supply voltage of transformer. How do we represent this supply voltage? By using some ideal voltage source. So we are represented or we are model the supply voltage in a equivalent circuit of the transformer. And next one, I knew. So it is a I knew. So this current is a magnetizing current of transformer. How do we represent this magnetizing current of the transformer? Already I mentioned that this current gives some amount of the flux in a transformer, but not any power loss. So that it is represented with the reactance element of inductive reactance element of X0 or Xm. Okay, am I right? So this one is, so this magnetizing current of the transformer, so it is the represented, this one is the represented by X0 or Xm element. So here this is called as a magnetizing reactance of the transformers. Okay, and next one, iron loss. Okay, IW. So this IW is a iron loss component of the current, or it is also called the core loss component of current here. How do we model this current? Okay, this is a, it is modeled with the element of, already we have discussed. So iron loss component of current gives some amount of the power loss, but not any flux production element. To represent the IW current here, So that is represented with the element of, okay, it is the represented, okay, this one is the represented, okay, by the year R0 or X, that's sorry, RC element. So that is the resistance corresponding to core losses, or it is represented with the R0 or R0. So this magnetizing current in a transformer, okay, this magnetizing current. So this magnetizing current create the flux in the transformer. So this flux is treated as, so it is a phi 1. So it is the mutual flux, and also it is also called primary flux of the transformer, or it is also called the mutual flux of transformers. Got it? So this is a phi 1 is a primary flux or mutual flux of the transformer. And next one, in this case, this flux will induce the EMF in the primary winding as well as the secondary winding of transformer. So where E1 is a primary induced EMF, whereas E2 is a secondary induced EMF. So this E1 is the primary induced EMF of transformer, and where E2 is a secondary induced EMF of the transformer. So got it? So this vector sum of these two current, okay, no load current of the transformer. How do we get this no load current? It is the vector sum of magnetizing current and iron loss component of the current. So next one more parameter. So after that another parameter C. So it is a V0 and I0. So this I1 dash is a I1 dash. So it is a load component of primary current of transformer. Okay, so which is the which depends on the load current or load variations here. So we know that this I1 dash is equal to magnitude of the I1 dash. So it is the K times of the I2. Okay, got it? So next one, I1. So this is the primary current of transformer. So this primary current, so that is a I1 is equal to vector sum, the I0 plus I1 dash. Okay, it is the primary current of the transformer. And next another parameters, that is a R, this is the I2. So it is called load current or secondary current of the transformer. So in addition to this, okay, some the parameters also there. So that is a resistance R1, okay, R1. So this is the resistance of the primary winding, okay, resistance of primary winding of transformer. Now similarly R2 is the resistance of the secondary winding of transformer. So in next one, X1 element. So this is the leakage reactance, primary, the leakage reactance of the transformers. So this is leakage reactance in primary winding of transformer. So now here X2 is the leakage reactance in the secondary winding of transformers here. So it represents, okay, here. So this is it is not physical element. So this is the representation of the primary leakage flux, that is the phi L1, and it representation of the secondary leakage flux phi L2 here. So now total flux in the primary winding. So that is so total flux in primary winding, okay, in the primary winding of transformer. So how much total flux in the primary winding? Mutual flux plus also primary leakage flux phi L1. So this mutual flux induces EMF in the primary winding, which is E1. And this leakage flux, how do we model this leakage flux? By using the reactance element X1. Now similarly, total leakage flux, okay, total flux. So in secondary winding of transformer, secondary winding, so that is equal to phi maximum plus phi L2 here. So this is a total flux in the primary winding. So this is the same. Okay, phi m1 and phi m2 both are equal. So the same amount of flux links with the secondary winding. That's why it is treated as a mutual flux. So this flows in the primary winding only. This flows in the pi L2 flows in the secondary winding of transformers. Okay, all of you get it? So these are called quantities or parameters here. So how do we represent these quantities in the electrical circuit manner? That is known as a equivalent circuit of the transformer. So that how do we define the equivalent circuit? Electrical circuit representation of all the parameters by using simple circuit elements is known as a equivalent circuit of the transformer or equivalent circuit of any electrical machine. Okay. No, it's coming, Raj. Sham, video is coming. Just check it once. It's clear, I think. Is that clear, everyone? Sham, video clear రావట్లేదా? Audio, is it clear? Voice ఎలా ఉంది? Clear ఉందా? Okay. No, ఒక 2 days నుంచి సిగ్నల్ ప్రాబ్లం ఉంది కదా, కొంచెం డిస్టర్బెన్స్ ఉంటుంది అప్పుడప్పుడు. ఇప్పుడు ఓకే, రైట్. Okay, all of you get it? So how do we define the equivalent circuit? Electrical circuit representation of all the parameters by using simple circuit elements is called the equivalent circuit of transformer. Okay, thank you Pavan, Bhargav. So now let us draw equivalent circuit of the transformer. First one, we have a two major parts in the transformer, core and transformer winding. So there is a two windings, one is the primary winding and also secondary winding of transformer. How do we define the primary winding? The winding which is connected to the supply is called the primary winding, whereas the winding which is connected to the load is called secondary winding of transformer. So initially the primary winding of transformer, okay, here the primary winding of transformer, so is represented with the coil. Okay, this is a primary winding of transformer is represented or drawn or modeled with the coil which has n1 number of the turns. Okay, where n1 is a primary number of the turns. Now similarly the secondary winding is also represented with the coil, so which has n2 number of the turns. Okay, it is the n1 and n2. So it is a primary winding and secondary winding. So vertical lines between the two windings, okay, it indicates the limbs of the transformer core. So this is the simple. The transformer has two major parts. The windings are modeled with the coil and core is represented with the by using two vertical lines. So this vertical line indicates the transformer cores. Okay, got it? So now left hand side, okay, this side, left side, so we have taken as a primary circuit and right side we have taken as secondary side. So this one is, this is only for our convenience. If we want to take the reverse also, there is no problem. So now I have taken primary winding. So the winding which is connected to the supply. Okay, the winding, so which is connected to the supply is called the primary winding of transformer. Okay, this is the primary wind. So now it is a V1. So where V1 is a single phase AC supply. Okay, it is a single phase, the equivalent circuit of the. So that is a V1. So now let us draw. Okay, this is the current passes through the V1. Okay, it is a I1 amount of the current. Okay, here I1. So we know that. So this is a, it is a no load current flows in the primary winding only. Okay, but not in the secondary winding. So no load current flows in the primary winding only, but not in the secondary winding. So now that no load current branch, okay, represented. So it is a connected in the shunt branch. It has a two components. So one is a okay, magnetizing component of the current, and second one is iron loss component of the current. So this is a magnetizing current INU, and iron loss component of current is IWL. So how do we model this magnetizing component of current? So it is a model with the reactance element of X naught, and this is the model with the resistance element of R naught. Okay, we have discussed already. So this is a R naught and X naught elements. Okay, so this is about, okay, so it is a complete no load circuit of the transformers. We have discussed this part. So this is the X naught element, and also it is a R naught element here. So EMF induced in the primary winding, it is the E1, and EMF induced in the secondary winding is the E2 here. So it has a two components, that is a reactance is a R1, okay, and primary reactance is a X1 parameters, okay, R1 and. So now this is the R1 and X1. So it is I naught current, so that this current is a I1 dash, okay, load component of the primary current. Suppose if you apply the KCL at this point, so I1 is equal to I0 plus I1 dash. Okay, got it point? So next one in the secondary side, okay, here these are two parameters, that is the R2, the resistance, the secondary resistance, and also secondary leakage reactance is a X2 parameters. Got it? And load is the represented with the some rectangular box. So this is the load, the representation in the equivalent circuit. So current passes through this element, okay, when it is a close. So now current is a passes through the secondary winding of trunk. So this current is known as a secondary current or load current. So now terminal voltage, okay, it is a, this one you can treat it as a, the V2 is the terminal voltage of the transformers. Okay, got it? This is nothing but, so this figure indicates that is a exact equivalent circuit of the transformer. Okay, it is a exact equivalent circuit of transformers. Okay, this is the, let us assume it is a figure 1, exact equivalent circuit of the transformers. Got it point? So this is the electrical representation of all the parameters by using simple circuit element is known as a, this is the is known as equivalent circuit. Okay, all of it clear? Is that clear? Mention in the comment, everyone. Okay, all of it clear? How do we draw? exact equivalent circuit of transformer. Just wait a minute. Just wait a minute. I will tell you one thing here. Okay. Yes, Pavan. Advantages of the equivalent circuit: to simplify the calculations or to modeling purpose. Suppose if you want to design the machine, the first one we have to model all the elements, then only we can design the machine. That's why here equivalent circuits are useful to model electrical machines. Okay, so now any more questions about this equivalent circuit? So this is a equivalent circuit, but in this equivalent circuit, we have some questions. Okay, first question number one. Question number one. Okay, tell me any question. You have to ask this question. Rajkumar, ready, clear. Very good, very good. Sir, what is the importance of no load current? Okay, Joseph, I will tell you that part. Bhargav, other reasons. Actually, modeling of any electrical machine, equivalent circuits are used. Okay, there is a question here. Anyone can ask this question or not? A very important question in the interviews also. I will tell you that question. First, guess. Anybody guess that question? Yes, Pawan, you are correct. Why does, okay, here is the question number one is, why does no load current branch I naught branch is connected in parallel, okay, that's correct. Uma Devi, good evening. You are late today. Why does no load current branch is connected in parallel? Okay, next, any other question? Suppose this is also parallel, right? Okay, here is so this one is this no load branch connected across the primary induced EMF. So suppose here also we may connect, right? This is also one of the possibility. So to connect, this is also, suppose we are agree. So question is, suppose the if I naught is connected, for suppose if I naught is connected in parallel, then why it is connected, across, okay, primary induced EMF, okay, this is also another. So why not at this position? For example, here let us assume it is the position, or why not at these positions? Clear point? This is all are clear. So it is also parallel. It is all. Suppose, are getting my question? Suppose ఈ బ్రాంచ్ ని మనం ప్యారలల్ గానే కనెక్ట్ చేయాలనుకోండి. సో ప్యారలల్ గా కనెక్ట్ చేయాలనుకున్నప్పుడు ఇక్కడ ఎందుకు కనెక్ట్ చేయాలి? ఒకవేళ ఈ పాయింట్స్ దగ్గర ఎందుకు కనెక్ట్ చేయకూడదు? ఇది ఈజ్ ఆల్సో ప్యారలల్ కదా, am I right? సో ఈ R1X1 ఒక టెర్మినల్ R1X1 మధ్యలో ప్లస్ ఇంకొక టెర్మినల్ ఇక్కడ కనెక్ట్ చేయొచ్చు. ఒకవేళ ఈ ప్యారలల్ కనెక్ట్ చేయాలనుకున్నప్పుడు ఈ పాయింట్ కూడా ప్యారలల్ కదా, అంటే బిఫోర్ R1, after the R1, here after the X1. సో నువ్వు ఈ పొజిషన్ నే ఎందుకు కనెక్ట్ చేయాలి? ఇక్కడ కనెక్ట్ చేస్తే ఎగ్జాక్ట్ ఈక్వలెంట్ సర్క్యూట్ లో ఏం ప్రాబ్లం అవుతుంది? సో వాట్ ఆర్ ద డీవియేషన్స్ ఆఫ్ ఎగ్జాక్ట్ ఈక్వలెంట్ సర్క్యూట్? అర్గెటింగ్ మై క్వశ్చన్. సపోజ్ ఈ ప్యారలల్ లో కనెక్ట్ చేయాలనుకోండి, ప్యారలల్ కనెక్ట్ చేయాలన్నప్పుడు ఇది కూడా ప్యారలల్ అవుతుంది, ఈ R1 అండ్ X1 మధ్యలో కూడా ప్యారలల్ అవుతుంది. సో ఇక్కడ కూడా ప్యారలల్ అవుతుంది. సో ఇక్కడ ఎందుకు కనెక్ట్ చేయకూడదు? So this is my question. Are you clear my point? Are you got it my questions? Okay. These are the two important questions for the interviews and also competitive exams. Everybody will draw what is the exact equivalent circuit of the transformer. But our point of view, what we have to read per competitive exam point of view. So why it is connected at this point? Okay, why it is connected exactly across the induced EMF? Why not between R1 and X1? Got it? And before R1, suppose here is connected, then what will happen? Okay. Yes, Arshavardhan, that is a very important question. Now we will discuss that question. Question number 1. Okay, here. See, so why no load current? Why the I0 branch? Why I0 branch is connected in parallel? Okay, in parallel here. So this part, the first question is why no load branch is connected in parallel in equivalent circuit of the transformers. Okay, so first one, we know that the reasons one here. So there are the two reasons is there. So no load current flows in the primary winding. Okay, no load current flows in the primary winding only. Okay, and it is independent of the load current and load variation. The element which depends on the load is a the current which depends on the load connected in series, like it's shown in the series branch, and the element which is independent of the load, so that is as like a voltage. Okay, it is shown in the shunt manners here. So this is the one of the reason. Okay, first reason here. So this is a no load current flows in the primary winding, I naught, the no load current flows in primary winding, in the primary winding of transformer. Okay, winding of transformer, and it is independent of, okay, it is independent of the load current. Okay, load current, and so and our load current are load variations. Okay, load variations here, so that the element which depends on the load is shown in the series. For example, I1 dash is shown in the series. The element which is independent of the load, that's shown in the sent manner. Okay, as like I naught values here. And one more reason also there. So this I naught, so this no load current doesn't have any role. So this is a no load current, no load current. So doesn't have, okay, doesn't have any role, any role, doesn't have any role to transfer the power, to transfer power from primary to power from the source to the load. Okay, this is the source to load here. So which current has the load to transfer the power from source to the load? So what is the function of the no load current? The no load current or exciting current excite the primary winding of the transformer. So due to which flux will be created in the primary winding, which also links in the secondary winding of transformer. According to the Faraday's laws of electromagnetic induction, EMF induced in the primary winding as well as secondary winding of transformer. So function of the magnetizing current to create the flux, and function of the magnetizing current is a to transfer the, or actually, so to supply the power to the iron losses. That is the iron loss component of the current. So now which current has the load to transfer the power from source to the load? I1 dash current as the load. So this is a, this I naught, okay, note. So here I1 dash as role, okay, as role to transfer power. I1 dash is the responsible. Okay, this one is a I1 dash, so is responsible, okay, responsible to transfer power. So this is the to transfer the power from, okay, this is the from source to, okay, source to the load. Okay, that's why here it is shown in the and also it depends on the load. So that's why it is shown in the series manner, and this current is shown in the shunt manner here. All of you got it? Okay, Siddhant, good evening. Tom Sundar given some answer. I naught should be parallel because when no load current is connected, transformer should provide the core loss magnetizing current to produce the EMF in the primary winding. So that exactly correct. Siddhant Bey, good evening. How are you? Okay. Joseph, any reason not role of no load current? Actually, no load current is a magnetizing. Okay, what is the no load current? So it is a I naught vector sum of magnetizing current plus iron loss component of the current. So this magnetizing current create the flux, right? So this is the supply the power to iron losses. Okay, this is the role of the no load current. So now which current here? This I1 dash load component of primary current transfer the power from primary to secondary side, so that you can write the that is a power balance equation, power, so balance equation in the transformer. So that is the E1 I1 dash is equal to E2 I2 values here. So when E1 I1 dash, and if I naught is neglected, then V1 I1 is equal to E2 I2. Okay, got it everyone? Yes. So these are the reasons. Okay, reasons to connect that to shown in this parallel. Okay, so next one more question. So that is question number 2. Like, so why does no load branch connected across primary induced EMF, okay, EMF. So why not across supply voltage? Why not it across supply voltage? Okay, so this is also another question slide. Okay, why does no load branch is connected across the primary induced EMF instead of the supply voltage? Got it? Anybody? Any guess? Why not no load branch connected across the primary induced EMF? Okay, as shown in the figure. Why not this position? Suppose if it is connected across the supply voltage, then what will happen? Anybody? We answer this question? Okay, if not get it, listen. So we know primary voltage drop. So we know that the primary voltage, okay, voltage, so drop of the transformer, okay, that is represented with, so that is a I1, okay, I1 R1 plus, okay, so it is a I1 the X1, okay, this is a primary voltage drop of the transformer. So I1 R1 and I1 X1. So where I1 we can write, okay, here. So where, so this is a, so I1 is a vector sum of no load current plus also load component of the primary current of transformer. So let us substitute here. Let us assume this is a equation you can write. So therefore I naught plus I1 dash, okay, I1 dash, so multiplied by R1 plus I naught the plus I1 dash multiplied by X1. So now simplify this equation. So that is the I naught R1 the plus I1 dash R1 the plus is a I naught, okay, X1 the plus I1 dash, okay, it is the I1 dash X1 here. All are vector, okay, this is a vector drop. So this is also another vector drop, a vector drop index. So what about this drop? Okay, it is a, okay, this value is nothing but, okay, it is connected. So now here, so this is nothing but voltage drop, voltage drop. So due to primary resistance R1 corresponding to, okay, this is the corresponding to no load current of the corresponding to the no load current I naught. Got it? So now this branch, okay, it is nothing but, okay, it is a voltage drop due to, okay, this the voltage drop due to X1 parameter corresponding to, okay, this one corresponding to the here no load current of the transformer. All of you got it point? So now this no voltage drop due to the resistance corresponding to no load current. Voltage drop due to the reactance corresponding to no load current. Suppose if it is connected, okay, here. So this branch, okay, no load, if no load branch is connected, okay, if the no load branch, okay, no load branch is connected, okay, is connected. So here connected across the supply voltage, okay, here supply voltage instead of primary induced EMF, primary induced EMF, then the what will happen in the transformer? So then what are the deviations? Okay, what are so deviations of, okay, deviations of exact equivalent circuit of transformer here. Okay, that is. So first deviation, so that is a voltage drop due to the resistance. Okay, see, so this branch is connected, okay, previously, okay, in this case instead of here, so this branch is connected at this position. What will happen? So no load current passes through this element, okay, it is a I naught current. So no load current doesn't flows through R1 and X1 element. Got it, point? సో మీరు ఇక్కడ కనెక్ట్ చేస్తే నో లోడ్ కరెంట్ ఈ పొజిషన్ లో ఫ్లో అవుతుంది. ఓకే, అలా కాకుండా ఇక్కడ కనెక్ట్ చేస్తే ఏమవుతుంది? నో లోడ్ కరెంట్ passes through R1 and X1 element. Similarly, I1 dash also passes through R1 and X1 element. Okay, got it, point? Okay, so what is the answer for this question? See, so here if no load branch is connected across the supply voltage instead of the primary induced EMF, then what are the deviations of exact equivalent circuit here? So first one, voltage, okay, drop. So due to resistance, due to primary resistance R1 corresponding to, okay, here, so this the corresponding to no load current I naught, the is not consider, okay, not consider. So this is the first deviation. Okay, now similarly voltage drop due to reactance corresponding to no load current, so is not consider, okay, not consider. So under loaded conditions, okay, under loaded condition, this is the very important. So we have to mention the loaded condition. Why? Because this X1 parameter, the present in the transformer under loaded condition. So under no load condition there is no X1. Why? Because leakage flux is negligibly zero. So X1 comes into the picture when load is connected. It represents the leakage flux. Okay, so that's why voltage drop due to the reactance corresponding to no load current is neglected, is not consider. Okay, it's not the consider. So under loaded conditions, okay, it is a loaded condition. Okay, got it, my point? So why this one is a under loaded, so condition of the transformers. Okay, and any other reasons here? Third reason, the no load primary copper losses. Okay, that is a no load primary copper losses of transformer. Okay, copper loss of transformer are not considered. Okay, these are not considered here. So this is a I naught square R1. This is nothing but no load primary copper losses of transformer. So in order to consider, okay, this one is, so what do you note here? So in order to consider all the drop, okay, all the impedance drop corresponding to no load current, so this is a, so in order to consider voltage drop due to, okay, voltage drop, in order to consider voltage drop corresponding to no load current, in exact equivalent circuit. So this shunt branch, shunt branch must be connected across primary induced EMF. Okay, all of it clear now? What happened, Pawan? Sir, please repeat. See this diagram. ఇది నో లోడ్ బ్రాంచ్ కదా. ఈ బ్రాంచ్ నేను ఇక్కడ కనెక్ట్ చేశాను. ఈ పొజిషన్ లో నేను కనెక్ట్ చేశాను అనుకోండి. ఇది ఇక్కడ కాకుండా అప్పుడు ఏమైతుంది, కరెంట్ ఫ్లోస్ త్రూ దిస్ బ్రాంచ్ బట్ నాట్ R1 and X1. Whenever no current flows, there is no load current flows through the R1 and X1, voltage drop due to the resistance corresponding to no load current is not considered. So to consider total voltage drop corresponding to no load current, that is a total impedance drop corresponding to no load current. So this branch must be connected across the primary induced EMF instead of supply voltage. Yes, got it, Pawan? Okay, in order to consider the voltage drop, okay, corresponding to no load current, this branch must be connected across the primary induced EMF. So in exact equivalent circuit of the transformer, suppose if it is connected here instead of this position, the no load current doesn't flow through R1 and X1. That means we are not consider the drop in the exact equivalent circuit. Actually, the drop occurs in the exact equivalent, in the exact transformers. Yes, are you getting my point? What I am telling you? These are very, very important and also very useful for your interviews. Okay. Yes. Any more question? Any more questions? If you have any question, you can ask. Okay, all of it clear? Why it is reactance under load condition? This is also very important. See, suppose if no load, if it is a no load, if transformer under no load, suppose if transformer is under no load, got it? So then what will happen? So leakage flux of the transformer almost equal to 0. If there is no leakage flux, okay, here if there is no leakage flux in the transformer, so then what will happen? So there is no reactance, leakage reactance term, then this leakage reactance will be 0. Okay, here leakage reactance will be 0 only. Okay, it is a 0. So that means voltage drop, okay, here voltage drop due to reactance, okay, corresponding to that, this total current also equal to 0 here. So that's why this drop is available in the transformer, or exactly in the transformer, only under loaded conditions. Okay, so if it is a no load, there is no drop. So that's why here there is no deviation of exact equivalent circuit. So it is a valid only loaded condition. So that's why we can write under loaded condition what will happen. So under loaded condition. So there is a phi 1 dash and also pi 2. So pi 1 dash is a, so which links with some pi L1 and also pi L2 here. So this is the part of the phi 1 dash, right? This one is the part of pi 2. So got it, fine. So this is only possible. This can be represented with the reactance drop of I1 X1. So this is represented with the reactance drop of I2 X2 drop. Okay, got it? So here this drop is available in the transformer at what point? Under loaded condition. Under no load condition, there is no reactance drop. Reactance drop is equal to 0. So that's why we have to specify here under loaded conditions. Okay, Unacademy, voltage drop due to the reactance corresponding to no load current is not considered under loaded condition. But under no load, this drop is not exist in the transformer. Okay, very good. Joseph, you asked one question. Why not connected between R1 and X1? Suppose I will connect here at this point. Okay, it is a I naught. Okay, like. So what will happen? I naught current. Okay, just assume. So this is some part of the I naught. So here I naught current passes through. Okay, here R1 element. Okay. So it is here. This is the path of the I naught. Okay, got it? So but no current passes through this drop. Okay, this element. So that's why the voltage drop due to reactance, primary reactance corresponding to no load current is not considered under loaded condition. Under loaded condition. Yes, Joseph. ఓకే, ఇక్కడ కనెక్ట్ చేసినాం అనుకోండి, మీరు ఈ డ్రాప్ కన్సిడర్ చేసుకుంటాం. డ్రాప్ డ్యూ టు ద రెసిస్టెన్స్ కరస్పాండింగ్ టు నో లోడ్ డ్రాప్ అనేది కన్సిడర్ అవుతుంది ఎగ్జాక్ట్ ఈక్వివలెంట్ సర్క్యూట్ లో. కానీ ఈ డ్రాప్ ను మనం కన్సిడర్ చేసుకోలేదు. ఒకవేళ ఇక్కడ కనెక్ట్ చేస్తే ఈ రెసిస్టెన్స్, ఈ టోటల్ ఇంపిడెన్స్ డ్రాప్ కరస్పాండింగ్ టు నో లోడ్ కరెంట్ ఈస్ కన్సిడర్ ఇన్ ద ఎగ్జాక్ట్ ఈక్వివలెంట్ సర్క్యూట్. So it is a preferable position is it is connected across the primary induced EMF instead of across the supply voltage or in between the R1 and X1. Okay, got it? Clear, Joseph? So very important. If you know this, very useful for your computer exams. Okay, all of you clear now about this answer? Regular class run. So I will explain 1 2 3 point one more time also, no problem. See, what about this drop, Pavan? This is a voltage drop due to the resistance corresponding to no load current. So voltage drop to the reactance corresponding to no load current. Suppose if it is connected, okay, here, so this is a supply voltage V1, okay, and here this is the connected, okay, in this position. So here we are connecting no load branch I0. So it is a two component, okay, like this. Okay, this is the magnetizing current, and branch here, this is the R1 and X1 parameters like. So this is the supply voltage V1. Suppose if it is connected before the R1 element, so then what will happen here? So no load current doesn't flows through R1 and X1. So only which current flows here? It is the I1 current and it is a I1 dash. So voltage drop due to corresponding to load component of primary current is considered. but this no voltage drop due to the resistance, primary resistance corresponding to no load current is not considered in exact equivalent circuit of transformer. And second one, voltage drop due to the reactance. Okay, this no load current doesn't flows through the X1 element. So that voltage drop due to the primary leakage reactance corresponding to no load current is not considered under loaded condition. And no load primary copper losses are not considered. So in order to consider total voltage drop, okay, this is the total voltage drop corresponding to no load current. So in exact equivalent circuit, shunt branch must be connected across the primary induced EMF. All of you got it now? Yes, Pawan? Yes, got it? Everything. Very good. Okay, so now sometimes we have a question. So that is the either exact equivalent circuit of the transformer. Exact equivalent circuit of transformer refer to exact equivalent circuit of transformer refer to primary side. Okay, how do we get exact equivalent circuit of the transformer refer to primary side? Okay, we know that exact equivalent circuit of the transformer refer to the primary side. Okay, it can be obtained. Okay, here exact equivalent circuit of the transformer refer to primary side. So can be obtained. Okay, can be so obtained by transferring. Can be obtained by transferring the secondary parameters. By transferring secondary parameters from the secondary side to the primary side of the transformer. So how do we transfer? We know already the condition. So in order to transfer the resistance parameter from secondary to primary side, copper losses should be maintained constant. In order to transfer the reactance parameter, so this way, which one? The per unit reactance drop should be maintained constant here. So now after the transferring, then what will happen? See, so this is a after the transferring, okay, we are transferring the secondary parameters. Okay, it can be obtained by transferring secondary parameters. That means we have to make it as one equivalent circuit. Okay, so this secondary parameter is transferring to primary side of the transformers. So now we are transferring secondary parameters from primary side. So this is this one is primary induced EMF E1. So now secondary induced EMF, so E2 dash. Okay, it is a E2 dash values here. So primary induced EMF and secondary induced. So now this is the I2 dash, R2 dash, X2 dash, and also V2 dash. So got it fine. So now this is the V2 dash and I2 dash, X2 dash. So now how do we get these parameters? Okay, from this equation, so we can write C. Okay, I2 dash is equal to, so from above equivalent circuit, from the above equivalent circuit, so here this the we get, So first parameters, how do we get this I1, I2 dash? I2 dash is equal to, so it both are in the series, so that is equal to I1 dash. So where I1 dash is equal to, okay, so we know that k times of the I2, okay, k times of. So now it is the V1 is equal to, here V2 dash is equal to V2 dash, so that is equal to V1. So in terms of the k, you can write, so now it is equal to here the E2 by k, okay, E2 by k1. So next one, and how do we write? See, and R2 dash, we know R2 dash. How do we get this R2 dash? R2 dash is equal to R2 by k square, and X2 dash is equal to, so now it is a X2 dash the is equal to X2 by the k square values here. So this way the exam, so it is a, it can be obtained by transferring the secondary parameter from the secondary side to the primary side as shown in the figure, as shown in below figure. Okay, this is a, so exact equivalent circuit of transformer refer to the primary side. All of you got it? Yes. So next one, how do we transfer? Suppose exact equivalent circuit of the transformer. One more, the another possibility here, exact equivalent circuit of transformer refer to secondary side, of the transformer. Okay, so how do we obtain this refer to the secondary side? So it can be obtained, okay, that is the it that can be obtained, so by transferring okay, primary parameters from primary side to the secondary side of transformers. Okay, so how do we get that primary side to the secondary side? So simply here this we have taken equivalent circuit. So we are transferring all the parameters from primary side to secondary side. So that is a V1 is a here. Okay, V2 is the remain same. Okay, it is a V2. Okay, V2 here, and it is a I1. Okay, V2. So it is I2. Okay, and next one, this value is a R1 dash, X1 dash, and it is a I1 dash. Okay, now this is a V1 dash. So here it is a V1 dash. Okay, V1 dash. So all the parameters we are transferring from the primary side to the secondary side of the transformers. Got it? So now this is the I nu dash, okay, IW dash and I naught dash values here. So from which we can write, so from above equivalent circuit, so we get, so what is the these parameters? I1 dash is equal to, so in terms of the current in the secondary parameters, that is equal to I2. So next one, the X1 dash is equal to, okay, here V1 dash is equal to V1 dash, that is equal to E2. So where E2 is equal to, you can write, so it is a I1 by, okay, it is a I1 by K, okay, I2. So now E2 is equal to, you can write in terms of the transformation ratio, so that is a K times of the I2, right? So next one, R1 dash, okay, that R1 dash, so that is equal to K square R1, and X1 dash is equal to K square X1 parameters here. So now it can be obtained by transferring the primary parameters from primary side to the secondary side. So primary side to secondary side as shown in the figure. Okay, got it, all of you, everyone. Okay, all of you got it. How do we draw the exact equivalent circuit of transformer refer to the primary side? And how do we draw the exact equivalent circuit of the transformer refer to secondary side? Yes. So this is the V2. Okay. So E1 dash is equal to E2. So how do we write this one? I2 place, that is the K times of E2, or K times of the E1. Exactly. Joseph, what is the reason behind transferring the one side to another? If any advantage, I will tell you. That is a, see here in this branch. Okay, all of you see in this branch here R1, and it is a, okay, for example, let us take previous one, exact equivalent circuit of the transformer refer to the primary side. So what about this value? It is a R1 and here R2 dash. Now is it possible to add these two resistance? So there is a branch, okay, in between the R1 and R2 dash. Okay, similarly it is a X1 and it is a X2 dash. So in order, is it possible to add these reactants in this equivalent circuit? No. Why? Because there is a shunt branch in between the X1 and X2 dash. So it is a very difficult. Okay, already I mentioned that. In order to find out the total copper losses in terms of the only one current. So that is the total copper loss refer to the primary side, total voltage drop refer to the primary side, total copper loss refer to the secondary side, total copper loss refer to the secondary side. How do we obtain? So if we know one current, it is a very difficult to find it. That means in order to simplify the calculations, we have to take some approximation equivalent circuits. Okay, so that is nothing but here. So first one, see, in order to, so this one is a approximation equivalent circuit. Okay, this is the approximation equivalent circuits. Okay, so this is a, here this the first approximation equivalent circuit. So it is the one is the first approximation. So what is the mean by first approximation? So in order to simplify, okay, this approximation equivalent circuits, so it is, see, approximation, the equivalent circuits are required. Equivalent circuits are required to simplify the calculations. Okay, to simplify calculations of transformer. Calculations of the transformer. So how do we get first approximation equivalent circuit? Suppose here there is a shunt branch, okay, in this case. So here I naught element. So next one, it has a two components. One is a, that is a magnetizing component of the current, and also iron loss component of the current. So now this is the shunt branch at this position. So it is the X naught and R naught element. So supply is here. Supply at this position, it is a applied voltage V1. Okay, clear my point? It is the I0 and I1 dash. Okay, I1. So here we are placing, so that resistance R1, okay, R1, and reactance is the X1, and the resistance parameter R2 dash, and reactance parameter, this is the X2 dash. So load is given here. So therefore this load resistance, the load terminal voltage V2 dash values here. Suppose if I take like this, then so what will happen here? I1 dash. So now here is a some current, okay, passes through I0 branch here. I1 dash passes R1 and X1. So therefore these two equivalent circuit can be modified as, okay, like, so supply voltage V1, okay, and no load branch parameters I0. Okay, it has a two components. One is the no load magnetizing component and iron loss component of the current. So now this one is a resistance, total resistance R01. That is the total reactance is a X01. So now how do we represent the load here? We can represent it by using one rectangular box. So now it is a V2 dash. So this current is a I1 current, and it is a I1 dash, and next one R is the applied voltage V1. So what are the advantages here? So we can calculate directly R01 is equal to, so R1 plus R2 dash, so that is equal to R1 plus R2 by K square. And here R0 X01 is equal to the X1 plus X2 dash, that is equal to the X1 plus X2 by K square values. So what we conclude here, approximation equivalent circuits are required to simplify the calculation. So this is the first approximation equivalent circuit. Okay, first approximation, the equivalent circuit, okay, equivalent circuit that can be obtained. Okay, this is that can be obtained, or can be obtained by reconnecting. Okay, this is the reconnecting no load branch, reconnecting no load I0 branch across supply voltage, instead of the primary induced EMF as shown in the below figure, okay, as shown in the figure. So now this, because of this you can get total resistance and total reactance parameters. Okay. Okay, in order transferring means all the referring methods are required to simplify the calculation. Joseph, so previous class I have given this reason. Okay, in the previous class I have mentioned the reason. That is, the referring circuits are required to simplify the calculations. Okay, all of you got it? So now we have a question. There is one question here. So that is so what are the deviations of, okay? So there is a question here. The deviations of first approximation equivalent circuit. First approximation equivalent circuit of transformer. First approximation equivalent circuit of the transformer. What are the deviations of the first approximation equivalent circuit? Anybody? So see this circuit. What are the deviation? Already we have discussed this point. First approximation equivalent circuit of transformer. No load drops are neglected. Very good, very good. So first deviation is a the no load branch, okay, that is a voltage drop due to primary resistance R, okay, R1 corresponding to no load current corresponding to I0 is neglected, okay, neglected here, this part, very good. And second one, voltage drop due to primary reactance, okay, corresponding to no load current is neglected, okay, neglected at what point? Under loaded condition, under loaded condition, okay, under. And third one is a whole year no load primary copper losses, no load primary copper loss are neglected, okay, these are I0 square R1, no load primary copper loss are neglected, okay. Any other? So these are some deviations of the first approximation equation. These are very important question, okay. Tomorrow we'll discuss the question based on these concepts, deviations of the first approximation equivalent circuit. Okay. So next one, the second approximation equivalent circuit. Approximation equivalent circuit of transformer. How do we obtain second approximation equivalent circuit? So it can be obtained by neglecting no load branch from first approximation equivalent circuit, okay, equivalent circuit of transformer. Got it, point? So if it is neglected, then it will become, so it is the only resistance R01, okay, and reactance is the X01, okay, this supply voltage, okay, V1, okay, supply voltage V1, and here you can write directly. So this current is a I1 current. So this is the load is a V2 dash, okay, V2 dash here. So this is per what? The refer to primary side, okay, here primary side. Suppose if we want to write refer to the secondary side, so then what will happen? So it is a V2. So now here is a V2, or this is the EMF induced in the secondary winding E2. So now this the resistance is a R02, X02, and also terminal voltage, load terminal voltage. So it is a V2 here. So current passes through here I2 amount of current. So this circuit is referred to secondary side of transformers. Okay, it is a EMF induced in the secondary winding. Okay, that is a here E2. Okay, E2 values here. Okay. Pawan, sir, in approximate circuit have no load branches connected nearer to the load side. That's why we have given, right? So it is a some deviations occurs. Deviations of first approximation equivalent circuit. What are the first deviation? Voltage drop due to the resistance corresponding to no load current is neglected. Right, Pawan? Second one, voltage drop due to the reactance corresponding to no load current is neglected under no load condition. And third deviation, the no load primary copper losses are neglected. Okay, these are the deviations of first approximation equivalent circuit. So here only these are neglected to simplify the calculations. So that I mentioned here, approximation equivalent circuits are required to simplify the calculations of the transformers. Okay, First approximation equivalent circuit can be obtained by reconnecting this I naught branch across the supply, instead of the supply voltage. So whenever these two are connected in series, R1 plus R2 dash. So now it is equal to X1 plus X2 dash, that is equal to X01. Okay, all of it clear? So this is the note, one note here. So this second approximation equivalent circuit, okay, approximation equivalent circuit is used to derive formulae for voltage regulation of transformer. Regulation of transformer. So this is the important point. Here, where do you can use second approximation equivalent circuit here? Suppose by using exact equivalent circuit or first approximation equivalent circuit, we cannot derive the voltage regulation formula. Suppose if you use the approximation equivalent circuit, we can derive voltage regulation of the transformers. Yes. Okay, any more doubts? Very, very important topics. Tomorrow we'll discuss many questions based on this concept. Okay, please be attend. Don't miss the class. Okay, we have a many question based on this concept. That is a three winding transformer. How do we draw the equivalent circuit of the? This is the only equivalent circuit of the two winding transformer. So how do we draw the equivalent circuit of the three winding transformer? So that part also we'll discuss tomorrow. Based on the problems, we have some problems based on the three winding transformer. Okay, inform your friends, don't miss the class tomorrow. Very, very important class, and we have a many question based on this concept. Okay, ready? You can ask what doubt. Doubts are always welcome. Joseph, are you clear now? జోసెఫ్ ఎందుకు రెగ్యులర్ గా రావట్లేదు, క్లాస్ నచ్చట్లేదా? How transformer act as the feedback circuit? Not feedback circuit, it is a negative feedback circuit. Ready? Your question is not feedback circuit, negative feedback circuit. So that part I have explained in the concept of the transformer under loaded condition. Just to refer my lecture, concept of that the transformer under loaded condition. That question I have already explained. Okay, if not, suppose not get it, tomorrow class we will discuss that part. Transformer act as a feedback, not feedback, negative feedback circuit. Why? Because pi 1 dash opposes pi 2. Actually, negative feedback means the output. Okay, in order to get the output, the input is the one of the reason. That output opposes the input. That is nothing but negative feedback generally. So here, in order to produce the pi 1 dash, pi 2 is the one of the reason. So this pi 1 dash opposes the pi 2 to satisfy the Lenz's law in order to maintain the stability in the system. So that part I have discussed very clear in the lecture of that operation of the practical transformer under loaded condition. Okay. Yes, ready. If not get it anything, then tomorrow class we'll discuss. Refer previous lectures, come regularly. మీరు ఒక క్లాస్ మిస్ అయితే కూడా మీకు నెక్స్ట్ కాన్సెప్ట్ లో డిఫికల్ట్ గా ఫీల్ అవ్వాల్సి వస్తుంది. మీరు రెగ్యులర్ గా క్లాస్ లైవ్ క్లాస్ కు రండి. వెరీ గుడ్. మీరు రెగ్యులర్ గా అటెండ్ కాండి, నేను కంపల్సరీ మీకు చెప్తాను. మీరు ఒక 1 డే చూసుకొని ఆ ప్లేలిస్ట్ లో ఉన్న లెక్చర్స్ ఒకసారి కంప్లీట్ చేసుకొని రెగ్యులర్ గా క్లాస్ అటెండ్ కాండి. రెగ్యులర్ గా క్లాస్ మిస్ అయ్యే కొద్దీ మీకు కాన్సెప్ట్ క్లియర్ ఉండదు. మీరు లైవ్ లో క్లాస్ వినడం వేరు, రికార్డెడ్ క్లాస్ వినడం వేరు ఉంటుంది. దట్టు మిషన్స్ లాంటి కొన్ని సబ్జెక్ట్స్ లో రీజన్ చాలా ఎక్కువ ఉంటాయి కాబట్టి మీరు లైవ్ లో ఉంటే ఇట్స్ క్లియర్లీ ఎవ్రీథింగ్. Okay. See here, all of you. This is our Creatrix official channel, which has 150k plus members. Okay. Join in the channel for any updates from the Creatrix. Okay. And the next one, this is our gate. Okay. So this is the Unacademy Gate Telugu Telegram channel. Okay. This is the here we will get all PDF class notes. Okay, every day. And the next one, what are the channels? The India's #1 studies channels. One is the Creatrix Gate and Unacademy Gate Mechanical, Unacademy Gate Civil. So Unacademy Gate Telugu. So this channel. Okay, please like, share and subscribe the channel. Okay, every day. ఫస్ట్ మీ పాయింట్ మీరు చేసేదల్లా కంపల్సరీ లైక్ చేయాలా, షేర్ చేయాలా, సబ్స్క్రైబ్ చేయాలి. ఓకే, am I right? Thank you, all of you. Okay, tomorrow morning. Okay, morning 11 a.m. So there is a special class in Unacademy. The topic is, so that is the three-phase circuit analysis. Okay, analysis. So in this, so voltage and current equations or the equations in the star connection. Okay, star connection. So what is the relation between the phase voltage and line voltage? What are the relations between the phase current and line current in the star connection? Already one lecture is completed in this topic. That is the generation of the three-phase voltage and three-phase current. Okay, if you want, see, this is a very useful topic for electrical machines concept, especially in the three-phase transformer and also synchronous machine and also the induction machine. If you good at this topic, you can analyze the remaining the electrical machine very easily. That's why I'm taking special class based on the three-phase circuit analysis. Okay, go through it. So you will get more from these lectures. Thank you all. We'll meet tomorrow at the same time.